Thanks for giving me the opportunity to speak here. So I'm going to talk about the isoperimetric inequalities, and it's related to some notion called Q curvature from conformal geometry. Okay, so let's start from the classical isoperimetric inequalities. On the planar domain, in 2 dimensions, it is well known that if I take a bounded domain omega, and its area enclosed by this curve, boundary omega, is bounded from above by some sharp constant 1 over 4 pi times the parameter of the boundary squared. And it is also known that when the domain omega is taken to be the ball, then this inequality becomes the sharp one. Well, what happens to the curved surface is, so for example, if we assume this surface is non-compact but complete, but without any topologies or without any holes inside, then as you can see that with the same boundary here, one can enclose a much bigger area inside. And because of that, one suspects that probably the bigger the positive curvature is, the bigger the area enclosed could be. So what is the right formula for the isoperimetric inequality on such a curved surface? Is that, let me come back to these slides a little bit later. So is that it is given by a classical inequality by Fiala and Huber. It says if you have a surface, and if you know that the positive part of the Gaussian curvature, its integral over the whole surface is strictly less than 2 pi, well, I'm going to talk about why this number 2 pi appears, then one has the isoperimetric inequality. Basically, the area enclosed by the curve is bounded from above by some constant. It's no longer 1 over 4 pi, as in the Euclidean case, but it is some finite constant times the parameter of the boundary squared. Well, here, as you can see that the integral of the curvature matters. So it's not a point-wise curvature assumption. And actually, this assumption, integral is strictly less than 2 pi, is a sharp one. Well, why is that? Well, let's come back to see this picture here, which is the simplest case because it's rotationally symmetric. So what happens is that you can think of this surface as a rotationally symmetric, as a cap, as a round cap, attached with some cone part. So over the cone, the metric is flat, so the Gaussian curvature is identically equal to 0. And over this cap, you can think of it as a part of the unit sphere, and therefore the integral of the positive of Gaussian curvature is determined by, the area of this cap part. So the area of the cap, because you count, so as the biggest case is that when you have this cap to be the hemisphere. So that's why you have this constant 2 pi there. That's exactly when you have the cap to be the hemisphere. Okay, so of course this theorem says that not only for the rotationally symmetric case, in general this is also true. Well, what happens when it's equal to 2 pi? When it's equal to 2 pi, you can construct this half-cylinder case in which one does not have isoperimetric inequality anymore. Okay, so the 2-dimensional case is quite obvious and beautiful, and another situation, well, which is related, is also talking about the relationship between isoperimetric inequality and integral of Gaussian curvature. Well, this is a little bit different. The setup is a little bit different. Here, instead of assuming the positive part of Gaussian curvature is strictly less than 2 pi, we assume the integral of the Gaussian curvature itself is less than 2 pi, which means that it could have bigger positive part, but there's some negative curvature which cancels that. Okay, so when that happens, one still has the isoperimetric inequality. However, this constant here is not a quantitative one in terms of the integral of curvature itself. So this could be depending on the metric itself. So here's the example that why this constant is not uniform in terms just of the integral of curvature. So basically, you attach a conical part with a cylindrical part, a cylindrical surface, and then finally you close it up by the hemisphere. And the distribution of the Gaussian curvature is like this. So over this conical part is flat metric. So again, the Gaussian curvature is 0. Well, it's negatively curved over those corners. And then it is flat again over this cylindrical part, and it is positively curved over the hemisphere. So what happens is that the integral of Gaussian curvature's positive part is equal to 2 pi, but it cancels out with some negative curvature over this neck, and then that's why it satisfies this assumption. As you can see that one can take this cylindrical part as long as possible, and that's why one does not have a uniform isoperimetric inequality. But with a given fixed metric g, which means that you fix some length of this cylindrical part, one has some finite number here. Well, that's a different phenomenon. It has a little bit less restrictive assumption. It has less. It has a little bit weaker isoperimetric inequality. So the question that I'm kind of interested is, what happens in higher dimension? What one can say in higher dimension of this type of isoperimetric phenomena? So, so it is known that the isoperimetric inequality under pointwise curvature assumptions in higher dimension what people usually study for higher dimensional manifolds. So the first question, okay, so here are some work. Huh? Right. Those are for manifolds, not necessarily. Yeah, so for Aubin and Cantor's result, they assume the sectional curvature. And for the later, it is less, it is becoming, those results assume the Ricci curvature. Okay, so the question that people are asking is that whether one can assume integral curvature assumptions instead of the pointwise ones, as people did here in higher dimensional case, just as what we have seen in two-dimensional situation. Well, as you can see, obviously the curvature could be infinity at some point. For example, in the rotationally symmetric cone case, but it doesn't matter. It doesn't influence the validity of the isoperimetric. All right. So another question, which is quite natural, is that in higher dimension, what should be the correct curvature to look at? Well, in two dimension, it's kind of obvious that everything boils down to the same one, which is the Gaussian curvature. But in higher dimension, there are many choices, like Riemannian curvature tensor, or Ricci curvature tensor, or scalar curvature. So a lot of choices in higher dimension. So the third question is kind of related to the uniformization theorem. So in two-dimensional case, even though what we were talking about is a non-compact case, there is sort of uniformization theorem by Huber back in the 1950s about what is the conformal structure near the end of such surfaces. And in higher dimension, of course, we cannot assume anything like that. But whether the conformal structure or a certain conformal class is related to the isoperimetric inequality is something that we are also interested in. Okay. So far we can answer these questions in the conformally flat case. And the right curvature to look at, so basically related to the question 2, is the Q curvature. Well, it's kind of hard to define Q curvature in short words, but let's say in dimension 4, the definition is this linear combination of higher order curvatures. Well, the leading order term is the Laplacian of the scalar curvature, and then plus 1/4 times scalar curvature squared, and then minus 3 times the traceless part of Ricci. So it's the leading order term is the 4th order in dimension 4, and then plus some combination of 2nd order curvature terms. Well, the reason that people define this is because it satisfies a certain analogous transformation law as the Gaussian curvature in 2 dimensions. Okay, so that's what I said here. So the Q curvature has analogous transformation law if you change a metric from G to some function times G, as that in Gaussian curvature in 2 dimensions. And another reason that we guess Q curvature is related to the isoperimetric is because Q curvature also appears in the Chen-Gauss-Bonnet formula in higher dimension, as that is the case for the Gaussian curvature in 2 dimensions. So because of those reasons, we're guessing that the Gaussian, the Q curvature is the correct notion to look at to deal with higher dimensional isoperimetric inequality. So here's the first result. So this is an analogous result as Lee and Tam's result in 2 dimensions in higher dimension. And so basically we need to assume this is within some conformal class of metric. And then we're looking at Q curvature to replace the rho of the Gaussian curvature. So basically the integral of, so Q curvature is integrable, and Q curvature's integral is strictly less than Cn, which was equal to 2 pi in 2-dimensional case, which is the integral of the Gaussian curvature over the hemisphere. And then with those assumptions, one has the isoperimetric inequality on such a manifold. So as the picture showed earlier, you could possibly, in this case, you could possibly have longer and longer cylindrical part. That's why this isoperimetric constant does depend on the metric itself. Okay, so another analog is the main result of that I want to say about it is the Fiala-Hilbert's type of result in higher dimensional case. Again, this constant Cn here is the sharp one. Okay, so as I said, this Cn was equal to 2 pi in 2-dimensional case. Okay, so here it says that as long as you have the Q curvature's positive part, integral is strictly less than Cn. And if you also assume the negative part of Q curvature is integrable, then you have the isoperimetric inequality. And this inequality, in this inequality, the constant only depends on those integrals of Q curvature. It doesn't depend on the metric itself, and depends on the dimension n. Okay, so here we assume a little bit more than the 2-dimensional case. So intuitively, the negative part of curvature should not make a difference of the isoperimetric. However, there's some technical reason that we need to assume the Q curvature's negative part is integrable. However, this number, as long as it is a finite number, it doesn't, it would not influence isoperimetric. All right, so let me say that when this sharp constant Cn is replaced by a small number epsilon. So basically, so this type of result was known if this CN is a very small number. And this is a result by Mario Bonk, Joha Hinonen, and Errol Saxon back in 2008. But we pushed these assumptions to the sharp ones in the above theorems. Okay, so let me finish by talking about what are related questions that that I'm still thinking about and I'm hoping to deal with. So basically, the general question that I want to ask is what happens in the non-conformally flat case, and over there, at least in 4 dimension, you will see some extra term which is the wire squared. So there's a type here. This should be wire n over 2. And this term appears when the conformal class is not conformally flat. And the question that I'm kind of thinking is that whether this wire L2 norm of wire tensor could play a role in the isoperimetric problem. And we're also thinking about what kind of more examples of wired isoperimetric behavior could appear when the wire tensor is non-zero. Okay, so let me stop here. Thank you very much.